Hello, everyone. I hope you're doing well. Last lecture, we introduced machine learning and all its applications, and we truly hope that you enjoyed that class. In this lecture, we will discuss a machine learning algorithm called linear regression. And as always, post your questions in the chat, and a TA will answer it. So now let me discuss my lecture outline. So I'll first start by just introducing the theory of linear regression. And then after I introduce the actual theory, I'll show you how to implement linear regression in practice. And the latter segment, so the second one will actually be optional, but we highly recommend you actually watch that. And before we actually start the lecture, I would like to discuss why exactly I like to start, or why many people like to start talking about linear regression as the first machine learning model that they introduce to students. And the first reason is that linear regression is a really nice model to really bridge the gap between statistics and machine learning. And indeed, if you look around, many introductory statistics classes do indeed teach linear regression. And secondly, and perhaps more importantly, is that linear regression is the techniques used in linear regression are really broad, meaning that they can be applied to many different machine learning scenarios. And whenever I introduce you to a concept in linear regression, which can be applied to many other different scenarios, I'll say that it's a broad machine learning concept, or as you can see here, I'll just it'll be written that this is a broad machine learning concept. So now that I've said this, let's actually get started on our discussion of linear regression. So what is regression? So regression is a form of supervised learning, meaning that you're given a bunch of labels and you try to generate you try to actually learn the rule from it. So it's a supervised learning approach wherein you try to predict a numerical output based upon a certain number of inputs. And let's make this a little bit concrete. So let's think of this situation. So let's say you're trying to predict a student's test score based upon the number of hours they spent studying for the exam. And this is a way you could do that. So one way you could do that is by collecting a ton of observations. So you can collect a lot of samples and then create a model which takes in the number of hours studied as input and predicts the test score as output. And the way you would create the model is by regression. So in this case, the input is the amount of hours studied, and the numerical output is the test score. So essentially, a regression is just creating the best possible function that takes in the number of hours studied as input and predicts a numerical output. So now let's continue our discussion of regression. But in order to do so, let's first start by just talking about just a few definitions. So as you can see here, let me 1 second. Yeah, okay, so as you can see here, when the student studied for 10 hours, he got a test score of 92. And when the student studied 6 hours, he got a test score of 89. And each of these samples, I guess, is called an observation. So in this case, each row in this table is called an observation. Secondly, now let's introduce the idea of independent or explanatory variable. So an independent variable labeled using X is just the input of the machine. It's just the input of the regression model. And in my opinion, a better word instead of an independent variable is explanatory variable. And that's just because these are the variables which explain the numerical output. So in this case, it explains the test score. Now, each observation is indexed using the observation number I. And that's just a fancy way of saying that this is x of 1, this is x of 2, this is x of 3, this is x of 4, on and on and on. And in here, in that y, this is y sub 1, this is y sub 2, this is y sub 3, this is y sub 4, on and on. So that's just how we index it. So now let's now introduce what our goal in linear regression is. So first, before I explain what the goal is, let me first talk about maybe the formal definition the textbook definition of the goal of regression. So if you Google in textbook, you'll probably see that the goal is to learn a general mapping f such that f of xi is roughly equal to yi. And that definition might make a little bit of sense, but let me explain it in greater detail. So essentially what they're trying to create is a function that takes in these x values as inputs and predicts the test score as output. However, it's almost impossible to get a model to do this correctly every single time. So therefore, we want to find a general mapping. That means we want to find an approximate function which takes in some input and approximately gives some output. It doesn't have to be perfect. And this is a big idea in machine learning. So in regression, you don't actually have to be perfect. And you want to create an approximate model. Okay, move on. So now let's talk about what linear regression is. So far, we just introduced a broad concept of a regression. So linear regression is when the function is a linear function. And another way of saying that is that the mapping from x to y takes the form of a linear equation. And linear regression is a very powerful technique. But there's two types of linear regressions. So one is simple linear regression, and the other is multiple linear regression. So simple linear regression is essentially linear regression when you have exactly one input. So if you're trying to predict the test score based upon the number of hours studied, that would be simple linear regression because you have one input. However, in order to predict many complex phenomena with good degree of accuracy, one thing that you might need, you probably need more than one variable. And to do that, that's multiple linear regression. So simple linear regression is when you have one variable, and multiple linear regression is when you have more than one variable. All right? And most of the lecture will focus on simple linear regression. And interestingly enough, multiple linear regression is a very natural extension to simple linear regression. So we'll only maybe focus 5 minutes on multiple linear regression. So now, in order to start a discussion of simple linear regression, recall from your algebra class that a straight line with one input is generally described by y equals mx plus b, where m is the slope. So recall from algebra that slope is, I guess, your change in y over change in x, so your rise over run, and your b is the y-intercept. That is when your line intersects the y-axis. So basically just basically the value of the line when x equals 0. And you'll see why this is useful in just a second. So the big idea of simple linear regression is that you want to find the best linear line that models these observations. So pretty much you're given a lot of these observations, and you want to pretty much find the best possible line best possible linear line to model these observations. And as I said before, there's pretty much no way that you can actually get a linear line to actually go through all of these points. And mathematically, what that means is that you won't be able to find a line such that y sub I equals m times xi plus b for each I. So that's just what it means. That's just the mathematical way of saying what I just said. And in particular, most of the time there will be a small error between the actual prediction, between the prediction and the actual value. And we call this deviation error. Okay, so the deviation for each of these points is called E sub I. And most of the time there will be this small error. And we want to pretty much find a line which fits the data as good as possible. And another way of saying that is we want to find a line which minimizes the error of the model. Okay. And in order to really quantify this, in order to quantify error and to determine how we can minimize this model, we need to introduce the notion of summation notation. Okay. So summation notation is seen seen pretty much everywhere in machine learning. And not only do you see this in machine learning, you see this pretty much in any field, in pretty much any science and engineering field. So in most of your coursework so far, you only had to add maybe a handful of values. So maybe your teacher said, what is 1 plus 3 plus 6? And you say 10. But what if you wanted to add a lot of integers? Let's say you wanted to add the first 100 or the first 64 integers, okay? So how exactly would you sum the first 64 integers? How exactly would you tell someone to sum the first 64 integers? So one way you could perhaps do that is just say, well, 1 plus 2 plus 3 plus 4 plus 5 plus 6, and just write every single value, write all 64 values, right? But that's very tiring. You don't just want to write all 64 values. So instead, what's commonly done is just people just use these dots. So if you wanted to sum the first 64 numbers, you would just do 1 plus 2 plus 3 plus 4 dot 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 up until 64, and just generally assume that the reader understands what that is. However, let's consider this. Let's say someone said, what is 1 plus 2 plus dot 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 up until 64? And generally, and most people would probably think, well, this is just 1 plus 2 plus 3 plus 4 up until 64. But if you're careful, you might know that 64 is 2 to the 6th, 2 is 2 to the 1st, and 1 is 2 to the 0. So one might even, well, one could quite naturally think that this summation is 1 plus 2 squared plus 2 cubed plus 2 to the 4th, all the way up until 2 to the 6th. And so this is ambiguous. How exactly can we fix this ambiguity? Luckily, we have a precise mathematical notation for writing the sum. And this is what's called summation notation. So, so in this case, if you're trying to add the first 64 integers, you would use this notation. So the sum from I equals 1 to 64 of I. However, if you wanted to find the first 7, if you wanted to find the first 6 powers of 2, so 1 plus 2 plus 4 up until 64, you would use this notation. Okay? And now let's actually see how the summation notation works. So the sum from I equals 1 to 100 is you just go from I equals 1, you plug in 1 here, and you have 1. Next, you increment this you increment 1 by 1, so you get 2. Next, you increment 2 by 1, you get 3. You increment 3 by 1 to get 4. And you keep doing that until you reach this value, which is 100. So this is just 1 plus 2 plus 3 plus 4 plus 5 up until 100. So another example, let's consider this example. And this is the sum from I equals 1 to 10 of I squared. So if first of I equals 1, we plug it in there, we got 1 squared. And then we increment I by 1 to get 2. We put in here 2 squared. Then we increment 2 by 1, we get 3 squared. And we keep doing that until we go to 10 and we have 10 squared. Okay. So now we're done with summation notation. So let's back to our discussion of a simple linear regression. Okay. And so note that for each, recall that for each observation, we define the error, okay, as the difference between the observation and the predicted. So another way of saying that is for each observation I, the error is the actual value minus the predicted value. Okay, and note that what we wanted to do was we wanted to minimize this error. But how exactly can we quantify this error, right? It's error. So intuitively, one thing that you might do is, well, you could just sum up all the errors, and then that could be a way that you could quantify the model error. But this isn't very accurate. And while that intuitively might seem true, that adding up all the errors would actually be a good estimate of a model error, actually it's not very good. And in order to see why, let's consider this example. So let's say you have two observations. One is 60 above the predicted line, and the other is 60 below the predicted line. So if you computed the sum of the errors, so 60 minus 60, you see that, well, there's no error, there's 0 error. And you might say, well, let's go, my model is working perfectly. But that's just not the case. It's just that your errors are in opposite directions. So in reality, I guess you have 60 plus 60 equals a 120 error, okay? So how exactly can you combat this problem? So one thing you might notice is that the only reason that this isn't working well is that you're just adding you're adding a lot of things which are of different signs. So you're adding positives and negatives. So one thing you want to do is just add up a bunch of positive errors. And luckily we have a function to do that. If we add up the absolute values of all the errors, then we have what we desire, the actual total error. So we add up the absolute values of all the errors, and that's a pretty good estimate of the model error. And in order to find the average error, you just divide the entire error by the number of observations. So you have 1 over n times the sum from I equals 1 to n of E sub I. So this is what I just said using summation notation. And however, there's another way to do this. And recall from before that the reason we did the absolute values is to make all the errors positive. And another way to make all the errors positive is to just square each of the errors. Squaring them will also make it positive. So in order to see that, for example, let's consider minus 2 squared. That is a positive number 4. And plus 2 squared is also positive number 4. So whenever we square a quantity, it becomes positive. So another way what we can do is we can take each of these errors, square them, and take each of these errors, square them, and add up the squares of all, and add up all the squares. So we take this, we square it, we add it to this squared plus this squared plus this error squared plus this error squared, on and on. And then we divide by n to sort of get the average error. And this is called the mean absolute error, and this is called the mean square error. And generally in machine learning, we don't really call this model error. Instead, we call this the cost function. So we call this model error function the cost function. And again, the cost function is pretty much how bad the model is doing. Okay, so let's move on. So pretty much what we have done so far is we have created these two functions which measure the error of the model, and you're trying to find the best possible line to minimize this error. Let's move on here. And however, one thing that you might notice is since you have two cost functions, how do you know which one to use? And I guess the short answer to this question is that you generally use the mean square error cost function. And that's a lot more common that's more commonly used than the mean absolute error. And in order to see why, let's consider this. So for anyone who has taken calculus, the mean square error is actually a very common choice in machine learning because it results in a function that is differentiable everywhere, meaning that you can compute the derivative at all the points. And I guess in order to see that, this mean square error function is very similar to a quadratic or a parabola. And if you've taken calculus, you would know that a parabola is differentiable everywhere. And for the mean absolute error cost function, and it's not actually differentiable everywhere. And in order to see that, let's just consider how an absolute value function works. So if you think of the function y equals absolute value of x, it's actually not differentiable at x equals 0 because it's an abrupt switch. And whenever you have an abrupt switch, it's not differentiable. So because it's not differentiable everywhere, we use the mean square error cost function. And even if you haven't taken calculus yet, this is completely fine. This is optional content. Just know that the mean square error is a more common error metric or a more common cost function than the mean absolute error. So now, as I said before, our goal is to find the optimal set of parameters, m and b, which minimizes the mean square error. And essentially what we mean by that is we want to find the best possible line that minimizes the mean square error. And because note that and the slope m and the y-intercept b, it uniquely determines a line. So now we have all our now we pretty much have all our building blocks. So now let's build a model from the beginning. Let's see how exactly we can implement linear regression from start to finish. So in order to implement simple linear regression, the first step is often to collect data. And in many cases, this will be done for you, meaning that you already have all the data you need. And you usually use other researchers' data. But a lot of the times you'll have to query or pre-process the data to transform the data into something that you're comfortable working with. After you have collected and pre-processed the data, the second step is to split the data into training set and a testing set. So what does that mean? So the training set is all the data that's used to actually develop the model. And the testing set is all the data that's actually used to see how well the model is doing or to test the model. After you have split the data, our next job is to just develop or train the model. And training the model is just a process of finding the optimal parameters which optimize your cost function. So in the case of simple linear regression, this is just a process of finding the values of m and b, which minimizes this mean square error. And after you have the values of m and b, now you have the optimal equation, which you can then plug in values to actually get what you want. And now our fourth step. our fourth step is to actually test the model. So now using a set of data which was not part of the training, meaning that we use our testing set. So using the testing set, we measure how well the model does. And the goal of this is to see how well the model might perform when it's applied to new data points. So that's pretty much all that is to simple linear regression. So so these four steps are always used when implementing simple linear regression. And now that's it. That's all you have to know to actually start implementing simple linear regression in an actual application. So now let's move on. As promised, we'll talk about multiple linear regression. But before that, I would like to clarify some machine learning notation. So in this lecture, I've used a lot of notation that I have might have only fuzzily defined. So I would like to make the notation more concrete. So as mentioned before, the data is usually denoted by X and Y. So the X is the explanatory or the input variables, and the Y is just the dependent variable which you want to predict. So Y is what you want to predict, and X is the variables that explain Y. And in machine learning, the set of parameters is usually denoted by theta. So in the past, I've said the parameters were this M and the B. But in machine learning terminology, instead of writing the equation as y equals mx plus b, you write the equation as y equals theta 0 plus theta 1x. And note that these two equations are equivalent, are basically equivalent to each other, except instead of m, we use theta 1, and instead of b, we use theta 0. And now we call theta equal to theta 0 and theta 1. So theta is just a set which has theta 0 and theta 1 in it. So now, as before, we seek to optimize a cost function, often denoted by J. And we usually call this cost function, which is, as I said before, the model error function measuring how bad the model is doing. And this function is often denoted by J. So we usually call the cost function J. And it's a function of theta, which means that we input, that means that theta is input to the cost function J. And now it might not be obvious to see how theta 0 and theta 1 are inputs to this error. And in order to see this, let's consider this, okay? So this is our cost function. This is a mean square error cost function. It's 1 over n times the sum from I equals 1 to n of your error square. And recall that your error is your actual value minus your predicted value. And our notation for our actual value is y sub I, and our notation for our predicted value is y hat of theta, right? So this is y hat is predicted, and yi is the actual. And so the error is just yi minus the predicted minus actual. Now remember that our predicted linear regression model is equal to theta 0 plus theta 1x. So now we can substitute y hat of theta with theta 0 plus theta 1x. So now we have the 1 over n times the sum from I equals 1 to n of yi minus theta 0 plus theta 1x all squared. So now you can probably see how theta 0 and theta 1 is in the function theta, and now you're pretty much just trying to find the optimal values of theta 0 and theta 1. And how exactly, and now a question that might come to you is how exactly can you optimize, or how exactly can you minimize this function to get the optimal values of theta 0 and theta 1? And in order to do this, we have to use something called an optimization algorithm. And Dr. Willard will talk about optimization algorithms in the next lecture. So stay tuned for that. And now, as promised, let's learn about multiple linear regression. So a lot of times, in order to predict a complex phenomenon, you don't just have one input, you don't have just one variable explaining the phenomenon. A lot of times you have more than one input. So for example, in our test score example, if you're trying to predict a student's test score, the number of hours studied isn't the only thing that influences their test score. In fact, things like their score on their homework and things like that also influence the test score. So how can you conduct linear regression when you have an additional variable? And the answer is surprisingly simple. It turns out that a lot of things in multiple linear regression work out exactly the same as simple linear regression, except we just have to change our original equation from y equals mx plus b, or y equals theta 0 plus theta 1x, to an equation like y equals theta 0 plus data 1 times the number of hours studied plus data 2 times their score on the homework. Right, so pretty much in order to account for each of these additional variables, we have to extend the equation. So like in this case, our equation of for multiple linear regression will be y equal to theta 0 plus theta 1 multiplied by the number of hours studied plus theta 2 times their score on their homework. And if we add another variable, then it will be plus theta 3 multiplied by the other variable. So that's it for multiple linear regression. And this concludes the theory portion of our lecture. Now let's actually move on to let's move on to actually see how we can implement a linear regression in a computer. And as I said before, linear regression is usually implemented in the computer. We don't usually just do it by hand. And I'll be using the Python programming language to actually implement this. So let me, 1 second. Let's go to, this is Jupyter Notebook. So I'll be coding in the Jupyter Notebook, and I'll give you guys access to the Jupyter Notebook via Google Classroom. Okay, so just log on to Google Classroom, and I'll give you access to that after the lecture. So before I start coding, let's first see what problem we're trying to solve. Okay. So the problem we're trying to solve is as follows. Our problem is to predict a student's SAT math score, depending on their SAT writing score, their SAT reading score, and the number of students who have taken the SAT in the particular year from their school. So essentially, what you want to create is a regression model which takes in these three attributes as input, and which we aim to predict their math score as output. Okay, so let's actually do this in Python. So before we start pretty much any machine learning problem, let's import many of the libraries which make Python such a powerful programming language. So first I'll start by importing the pandas library. So the pandas is a library, so right here, so pandas is a library used for data analysis. For data analysis. So pandas is a very common library used in pretty much every machine learning application for data analysis. So wait, and by the way, before I actually move on further, can everyone see my screen okay? Yes?
Yes.
Good, okay, nice. So now first we've imported our data analysis library, pandas. Now let's actually import NumPy. So what is NumPy? So NumPy is a numerical computation library. So it's used for many of the numerical computation tasks we do in machine learning. So let me just write it down. So NumPy is a library used for numerical computation. So for the last library we have to import is the sklearn library. And it turns out that Python already has many machine learning models already inputted. So now I'll be importing linear regression, and this is actually the reason why Python is so powerful, just because you already have a library that has linear regression in it. So instead of manually implementing linear regression, which would take at least 50 lines of code, you can pretty much do all of linear regression in just 2 or 3 lines. So that's the reason why Python is so powerful for machine learning. So we have from sklearn, from scikit-learn, we'll take the linear model and let us import what's linear regression, right? Linear regression. Now we have imported all of our, we've imported everything we need to actually get started. So now let's actually get started with our discussion with this. So now what we want to do is just get our Excel file and put it in Python. How exactly do we do that? So we use the read CSV function to actually get a file, get an Excel file or a CSV file more generally to Python. So and another thing is that when we actually put this in Python, the table. So we want to implement this, import this table into this Jupyter Notebook, and in Python this is called a data frame. So this data frame is pretty much a table. So you have df, we're going to pd.read_csv, your actual test score, right? So the file is called testscore.csv. So now I actually imported testscore.csv into the Jupyter Notebook. So that's nice. So now let's actually do analysis with it. Let's now conduct linear regression with it. So now in order to get a linear regression, first let's define what our x is and what our y is. So our x, in order to actually see what our x is in the beginning, let's think of what our features are going to be. So if we go back to our Excel file, what you'll see is that our features are test taker, reading, and writing. So these are our x values, and our y values is the math. So let's put that. So we have our features, right? So features is by another word for inputs, by the way. So our inputs or features are test taker column, the writing column, and the reading column, right? So these are our inputs, and our x is just df features. And what is our y? And interestingly enough, what our y is just our math score. Okay, so now we have our x and our y. So now we can actually start doing linear regression with it. And in order to start doing linear regression, let's import a sample, a template linear regression. So this is a template linear regression, which and you can put in your specific x and y values to actually get your specific, a specific value, right? To actually get your specific equation for your case. And luckily, Python does the entire training process in just one line. We use the lr.fit function to actually have our x and our y, okay? So now when we use the lr.fit function, what we should see is that we should get an equation of the line. So let's run it to make sure that everything is correct. But, sorry. But when you get it, you actually get an error, right? So you say that input contains NaN, infinity, or values too large to be a float. Why exactly do we get that error? And if you go back to Excel, what you know that you have a lot of these missing NaN values. And we want to have, and the computer can't just add NaN values or subtract NaN. It can't do computation with these NaN values. So it's just giving out an error. So how can we deal with it? So what we want to do is replace the NaN with, we can either drop it or we can replace it with something else. So in this scenario, I'll be replacing the NaN values with the mean of the column or the average of the column. So another way of saying this is I'll replace this with the average of this column. I'll replace this with the average of this column, on and on, okay? So let's do that. So before we replace our NaN values with the average of each column, let's first just compute the average in each column, okay? So we have an average in our mean test taker. So the average in our test taker column is just our df test taker. So our test taker column dot mean. And this dot mean function ignores all the NaN values, okay? So when it adds everything up and divides, it doesn't consider the NaN values. So now let's do that for all of our other 4 columns. So we have first, our next column is mean reading. Yeah, so mean reading is df reading dot mean. Mean writing is df writing dot mean, and our mean math is df math. Okay. So now we have computed. Sorry, one second. So now we have computed all of these values. Okay. So now that we have computed all of these values, we want to replace each of these mean values. We want to replace NaN values, the NaN with the means. And just for a sanity check, let's just make sure that our values are actually okay. So let's just print. So just for sanity check, let's just see if we actually computed the mean correctly. And 110, that seems pretty reasonable for the test taker column mean. Now I'm assuming everything looks good so far. So now what we want to do is replace the NaN values with our actual mean. So we have our test taker. So first let's do it for each of our 4 columns. So we have our df test taker, and we replace it. Okay? So we replace it with MP. So we replace our NaN, np.nan. Let me talk about what that means later. We replace our np.nan with with our mean test taker. And it looks like, just one second, looks like we have a lot of questions, but I'll get to the questions after, okay? So I'll replace the test taker column, I'll replace the NaN with the mean test taker. And it turns out that you can't just type in NaN like this. It doesn't work. So NaN is actually a special function. You have to invoke numpy, empty.nan. So let's do the same thing for all other 4 columns. So we have mean reading. Let's do mean reading. Let's do the same for writing. Mean writing and mean mapping. Now we're done with all the replacing. But one thing you have to consider is that in order to actually update the actual data frame or the actual table, what you have to do is you have to do the in place equals true. That's an optional parameter. So in place equals true. Okay, so let's do in place equals true. So now we have most likely replaced it. But in order to see that, let's just go df. Let's type in df df.head. Let's go 30. So what df.head 30 is that it's just the first 30. It's just the first 30 rows in the table or data frame. And it looks like we don't have NaN values, so I think we're successful. So now that we have taken care of these NaN values, we can start our analysis, right? We can start our linear regression. So let's copy paste this code back in, and now we should expect it to work. So let's run it. But we again have an error. What's that? So let's see what the error is. So as input contains NaN infinity or values too large to be a float. And the reason we actually get these errors is that recall that x here is our x from before. So x from before we actually replace these values. So now we again have to define x with the data frame which has these values replaced. So let's copy it and let's paste it to actually get our new updated set of x and y values. So now when we do this, this should work, okay? So now we command V it, so we run, and now it works. Now we expect an equation, but when you run this output, you don't really see an equation. And in order to see the equation, you have to use 2 other attributes to actually look at the equation. So now if I go back to this slide, note that theta 0 looks different from theta 1 x1, theta 2 x2, and so theta 0 is different from theta 1 times this, theta 2 times this. Okay, so it looks different than that. And in Python, we call theta 0 the intercept, and we call theta 1, theta 2, theta 3, theta 4, up until theta n the coefficients. Okay, so let's find that. So I guess in order to make it more concrete, let's do lr dot intercept. Make sure I'm spelling it correct. So now when we do that, we get this value. So we get this theta 0 value, okay? And when we do lr dot coef, you get the values for all our other parameters. So you get your theta 1 values, your theta 2 value, and in this case, your theta 3 value. So that's nice. So now you have the equation. So let's just write our equation, right? So we have y equals, we have our first intercept term, plus this value multiplied by the number of their test takers, so the number of test takers, plus this value times writing times their times individual's SAT writing score, plus this multiplied by their reading score. Okay, so this is your equation. So now given a few values, you can just input their test taker, writing and reading, and you will automatically get their SAT math score. So this is our multiple linear regression model. And the thing that's so cool is that I've done an actual application in just 20 minutes, or maybe not even 20 minutes, like 10 minutes. So that shows that really shows how powerful Python is as a programming language for machine learning. So now you might want to predict something. So let's say a student. Let's say there's a student who has 125 people who took the SAT in their school, has a 600 score on the writing and a 500 score on the reading. So we want to predict. What this student would get on the SAT math according to our model. And luckily, we have a function to do that as well. So let's have x predict. So our x values is 125. Okay, 600 and 500. Okay, so these are our x predict values. So now we can use the dot predict function, LR, so our linear regression, dot predict. Now if you give it x predict, it'll automatically tell you what your y is. So in this case, what your SAT math score is. And if you do that, you get 577. So that's really cool. So now you can do this for every single case. So now one caveat is that in a real scenario, what we would most likely do is, so in this case, what we did is we skipped, let's go back here. Yeah, so we skipped step 2. So we never really split the data into training sets and testing sets. But in a real application, you would indeed split it into training set and testing set. And luckily, you could easily do that using Python. So you split it in training and testing set, and then actually develop the model just using this training set, and test the model using the testing set. And you would use a quantitative metric to actually test your model. And we'll learn more about these quantitative metrics in lecture 8. Okay. So that is it for our lecture. And one thing I would like to note is that there was a lot of information here. So what I really recommend all of you guys doing is maybe view this recording a couple more times to actually internalize the concepts. And I really recommend that. And we will be posting this recording in Google Classroom. So that is it for this lecture. Now I'm open to any questions. Any questions?
I have a question. Yes.
Yes.
So I was wondering, in the Jupyter notebook, or using Python in general, can you create a graph of the actual equation?
Yes. Yeah, you can create a graph. Yes. So there's a library called matplotlib, and so Google that. Okay. So when you get home, or at your home right now, sorry. So just Google matplotlib or GNU plots in general. And when you Google matplotlib, you can see how exactly you can plot a function. So yeah, so Python can pretty much do everything that you can think of. Yeah.
Okay.
Yes. Yeah, so we use the matplotlib function to do so. Yeah, it's possible. Any more questions?
There are a couple questions in the chat. So if you want
chat. Completely forgot about that. Okay. Chat. 35 questions. Ooh. So first question. Are there any other number values that can be inputted to replace them? I believe okay. So Ashani said, are there any other number values that can be inputted to replace the NaN values? And I'm not okay. I believe there is, but again, So mean is the most common metric that you use, but another common metric is just drop the NaN values altogether. So that's another common metric. So pretty much the two most common things, Shani, is that is to either replace the NaN values, either to replace the NaN values by just replacing it with the mean, or by just dropping the NaN values altogether.
It's also possible to use the median sometimes. It really depends on the application.
But for the most part, I usually just use the mean. Yeah. See, there's more questions. So would you 75?
That's in reference to an earlier question about the training and testing split of data.
Okay, wait 1 second. Training and testing split. Okay, oh yeah, okay, I see it. So is 80% and 20% a good data template, or are there any? Yeah, so Dr. Willard answered it pretty well. So yeah, as I said, it depends on the volume of, yeah. Yeah, exactly, yeah. I think Dr. Willard answered it pretty well. 90-10, I usually, 90-10 usually isn't recommended, but so 80-20 and 75-25 are some pretty popular ones. So Kavya, can we use 0 instead of NaN? I wouldn't recommend using 0 instead of NaN, just because it just skews the data. It's a lot better if you just use the mean instead. Because instead of 0, what you can do is just replace the values. So 0 would be a very inaccurate, um, a very inaccurate value. So for example, let's say you knew that the student got a 96 on the test, but you didn't know how many hours they studied, and you just had 0 as the approximation. That would most likely be wrong. So I would just not do that. I would just not put 0. So says Thomas. Oh wait, will the homework assignment for this class have us use the Jupyter notebook and predict? No, actually no. For this class, the assignment for this lecture will be a multiple choice. Will be a lot of multiple choice questions, but a few of the questions in the multiple choice will entail to the programming. Everyone can unmute. Yes. Yes. Wait. Rishi, yes, it would essentially be making up data, but our goal is to find the best approximation for NaN. So you would be right. It would essentially be making up data. But what we want is since we don't know what the NaN values is, our goal is to find the best possible approximation for the NaN values. And a lot of the times, a mean is a pretty good approximation for the NaN values. Does the IDE PyCharm work as well? Yes, it actually works quite well. Yeah, I believe Strawman actually uses PyCharm. Yes. Any more questions? Yeah. So as Strawman said, you can just unmute and speak up as well if you want to.
Just to add on, I mentioned in the chat that I use Spider, which is also very common for Python development.
Collab is also good. It's free. And yeah. Yeah. So pretty much any IDE works. Like yeah.
Okay. Hey Shreyas, I was wondering, going back to the theory of the linear regression, like mathematically, why is it important to have it be differentiable?
So the reason it's so important for it to be differentiable is that so as Jeff or as Dr. Willard's going to say tomorrow, a lot of the optimization algorithms rely on differentiation to actually work. So when a function isn't differentiable everywhere, it leads to problems in optimization algorithms. So I guess the short answer is that optimization algorithms don't work as well.
Okay. Yeah.
Oh yeah, any more questions? Let me look at the chat.
Shreyas?
Yeah, Rishi?
So also about the cost function, I was wondering, so it said it's a function of theta.
Yes.
So to be inserting a value for theta, or is theta just representing like a arbitrary value?
Yeah, so theta is just so in function notation, theta is just representing an arbitrary value. So that means that you can plug in theta into the equation. So basically saying that, so what we mean by j is a function of theta is that the cost function has theta in it. Okay, does that make sense?
Yeah.
Okay, nice.
And we'll talk more about cost functions on Tuesday during the optimization lecture.
Yep. Yeah, so cost functions are used in a wide variety of machine learning problems. So in a lot of the lectures, we will be referring to cost functions. Yeah. So anything else? Boom, I see a chat. Will we be implementing a neural network without any machine learning libraries? It is possible to implement a neural network without any machine learning libraries, and in fact, it will be a very good programming exercise for you to do so. But I believe when you're going to be implementing neural networks in this class, we will be implementing machine learning libraries. Will there be any future programming examples showing data split? I mean, sure, if you guys want to. Yeah, I guess, yeah, sure. Maybe, yeah, sure. We can do that. Yeah, well, Tinish, definitely. We will post the regression code on Google Classroom. Yeah, so there's a train test split function on Python. I forgot the exact syntax, but there's a train. There does exist a function for that, and we'll talk about it maybe in a future programming exercise. What machine learning libraries will we be focusing on? So we won't really be focusing on any machine learning libraries in particular. Yeah, so we won't really be focusing on a machine learning library. It's just going to be, so the goal of this course is just to introduce all of you guys to the machine learning concepts. And there really isn't going to be a specific focus on the libraries. Maybe we might just continue with scikit-learn, but not sure. We haven't made a decision on that yet. Ooh, okay, nice. Any more questions? Okay, so in this lecture, we'll mostly be focusing on Python. We'll just be using Python in general. But if you would like, I guess you could implement some of these functions you could implement some of these models in Octave in your own time.
Shreyas, I'll try to get some examples put together in Octave as well.
Okay, so yeah.
Post to Colab, or not to Colab, Google Classroom.
Yeah. So yeah, Octave is actually Octave is a very nice language to actually learn, just because a lot of the machine, like you can directly see all the math. You can usually directly see all the math in Octave. So I really like Octave as a programming language for machine learning. But in here we'll actually be using Python. Trace and Dr. Willer, is it possible to post the Google Slides lecture? I mean, I guess, yeah. So we'll definitely be posting the recording, and I guess if you want, yeah, sure. I guess we'll be able to do that. What do you think, Dr. Willard?
We can do that. We'll turn it into a PDF first.
Yeah. Okay. So any additional questions?
Thank you very much, Shreyas.
Oh yeah, okay, thank you. Yeah. So I guess we're done with questions, and yeah. So in the next lecture, Dr. Willard is gonna introduce us to optimization algorithms. So look forward to that. The optimization algorithms are actually really cool. And another cool thing is that we're doing this all without calculus. So with that being said, see you in the next week on Tuesday. All right, bye everyone.